Hi y'all, welcome back. Let's go ahead and solve the last part of this worksheet. I know we have gone through a very long journey. So the last part, the worksheet is part G, and it asks which stress component is 0, and they ask us to compute the radial distribution. And torque. Okay, this is a very physics term. Torque needed to rotate the cylinder. Okay. Okay, so let's go ahead and find on the stress component. They only ask for the radial distribution though, but I would like to give y'all some insight about the other component as well. Okay, so let's go ahead and jump to equation 5.63, page 278. Let's see what we found. Okay, the first thing we notice is that they say the tau, right? What is tau? Tau is the stress component, okay? So tau phi z. Oh, you might wonder why it's phi z, because I'm not really sure, but I think this is more like a stress tensor thing. I think it's more like matrix stuff, so I'm not really sure, but it is depicting the coordinate, the direction the stress is having. I think tensor is an interesting thing to look at. So, all right, it's interesting to look at stress tensor. I think they explain better. They explain to you the direction and orientation and all that. Okay, but now let's follow the formula and see what it say. So this equal to tau of z theta. It equal to mu times the partial of u theta over partial z plus 1 over r times partial uz over theta. Okay, what happened to this component? Okay, you notice two things. Number one, uz is 0, so this term cancel out. Okay, let me write in blue. uz equals 0. And the second term cancel out as well because, okay, let me be consistent. Okay, I'll use this as blue. This cancel out as well because remember, u theta is not a function of z, it's a function of r. U theta is not a function of z. Therefore, derivative partial u theta over partial of z equals 0. Okay, so this stress component equal 0. How about the other one? So let's see. Tau zr is the same as tau rz, and is equal to mu times partial uz over partial r times uz plus partial of ur over partial z. Okay, what happened to this component is also cancel out because here uz is 0 and here ur 0 on this, so which indicate that on this equal to 0. So from to this you can implement that these are the two zero stress component. Okay, so how about a radial distribution? I'm just basically showing you guys that the other stress component rather than radial is 0. We just derive it here. So let's now we compute the radial distribution of stress. So I will write compute the radial distribution of stress. Okay, how do we do that? It's the same equation. I mean, it's the same table, but you move down. Okay, you say tau of theta r equal tau of r theta is equal to what? Mu times r times partial of with respect to r of u theta over r plus 1 over r times partial ur over partial theta. Okay, so is there anything you can cancel out? Yes, we can. This term right here go away because ur is 0. Okay, so now our expression is equal to partial of r times partial with respect to r of u theta over r. Okay, what is u theta if y'all remember? So u theta, we have the expression for u theta, right? I think let me go ahead and see it again. I'm pretty sure we have an expression for u theta for sure. U theta, yeah, there we go. This is expression for u theta. Oh, we got r squared over r. Okay, remember that with me. Okay. So we plug that in here. So equal to mu times r times partial with respect to r of omega r squared over r squared, right? Because you also divide by r. Okay, and then if you take this term right here with respect to r, partial with respect to r, you get mu times r times omega r squared times 1 over, what is r squared? What is 1 over r squared? Derivative is equal to derivative of r to negative 2 is equal to negative 2 times r to negative 3 is equal to negative 2 over r cubed. Okay, so negative 2 over r cubed. Okay, and you do some simplification, is equal to mu times omega r squared times negative 2 over r squared. So this is our stress component. Okay, it's a stress component. However, it is very important to take the absolute value to get the value. So you take the absolute value. So absolute of tau r theta is equal to absolute of tau theta r, and negative 2 become plus 2. So you come to mu times omega r squared times 2 over small r squared. Okay, this is the stress component. What about the torque? What is a torque? Okay, I will draw some picture out to explain it better for y'all. So let me write a question now. So what is the torque need to rotate the cylinder? Well, remember this cylinder, right? So this cylinder, we have this is the coordinate, right? This is the normal coordinate. This is the z coordinate. And let's say you have a cylinder right here. It's rotating, right? And it has an angle theta, and it has it had a length r, it had a radius r. Okay, so the width of this whole cylinder is from here to here. Okay, because we're talking about the cylindrical coordinate. But let us like zoom into the let us zoom into the whole this side right here. Let me draw it out for you. Let me zoom into this side right here. So let's draw a picture out. So okay, this is x, this is y. Remember, when you invent the coordinate, you start with Cartesian, right? And then you build up. You build up from Cartesian, you get the cylindrical. So it's also a good idea if you start drawing coordinate with x, y, z, and then you introduce theta and r. Okay, so but let's see what the cuts look like for our tiny nice cylinder. It looks something like this. This is y, this is x, right? And you have a random radius r. This point is big R. So this is the definition of level arm. Okay, this is This is definite. This length is the level arm. Okay. So what's the torque formula? The torque formula is equal to shear stress times area times level arm. Okay. So what is our area? Again, this area is the surface area. So our area right here is just 2 pi r times w. Okay. However, this, okay, I see. So w equal to 1, so it's 2 pi r. Because we are calculating torque per width. Okay, that's why it's just 2 pi r. It doesn't have w there. Okay, you with me? Okay, so the level arm. What about the level arm? Level arm is big R. Okay, how about the shear stress? The shear stress, we had it already, right? The shear stress is tau of theta r at points radius equal big constant r. Okay, so you have the shear stress ready. This term right here. You just substitute in big R to the denominator. So you get rho times omega. Let me just want to make sure. Okay, mu, not rho. Mu times omega times r squared. Okay. Mu times omega times r squared times 2 over, you substitute in, so you get r2, r squared, so you get 2 mu w. Omega, okay, this is omega. So if you time all these together, you get the torque equal to 2 pi r times 2 mu omega, then times r. So it will get you 4 pi r squared mu omega. Okay, and that is your final answer. Okay, that's the definition of shear stress. Shear stress, you have the level arm, you have the area, but this area is the area per width. So that's all you need to be careful of. This is our final answer. Thank you everyone for your attention, and I'll see you in the next video.